You'll start the recording, right? Make me a co-host when you get a chance there, yeah. I'll wait till I see the recording message come up, and then we'll begin, ladies and gentlemen. Well, good evening, ladies and gentlemen, and welcome to this monthly public lecture of Astronomy Ireland. You're all very welcome. I've seen people booking places from all over the country, north and south, and all points in between. My name is David Moore. I'm the editor of our magazine, Astronomy Ireland. And tonight we have a great talk for Space Week. This week is Space Week. There are events happening around the country. I've been giving talks earlier myself today and again tomorrow. And if you want to check out spaceweek.ie, you'll find this talk is listed along with many others for the rest of the week as well. Now, the format of the evening, for those of you who are new, will be we'll have a little bit about the past. These are our monthly meetings. All the members gather together from around the country. Non-members are extremely welcome. And then we'll have our main speaker, Dr. Mark Norris from the University of Lancashire, who's going to talk tonight about our cosmic origins. And then we'll tell you a little bit about what's happening in the future, both in the sky, some quite exciting events coming up, and very briefly, our next talk and two other events that we have on as well. So October is going to be really a packed month for us to get back into all the excitement, including that big comet that's coming, which I'll mention after the talk. So our last meeting was on September the 8th, sorry, 9th, wasn't it? September the 9th, which I'll come to in just a moment. But I want to tell you a little bit about what Astronomy Ireland does. We're the most popular astronomy society in the world, as far as we know. There are thousands of people all around the country, hundreds of thousands if you count all of our social media and email list followers. And we try to get people interested in astronomy. And we also produce Astronomy Ireland magazine every month, 48 pages of full colour, all the latest discoveries, especially with Irish angles, what to see in Irish skies, what people have been seeing in Irish skies. So don't miss that. It's a fantastic read, we think. At least just scan through it, looking at the pretty pictures every month. We also do these monthly lectures. Twice a year we have evening classes. They're actually coming up this month, I'll tell you at the end. And as well as that, then we have watches where we set up telescopes, usually in the Leinster area. We are trying to expand that around the country and get funding for that, probably in the new year. But we're going to set up telescopes for Saturn this month, and I'll tell you briefly about that. You have to rush off. It's on the website, which is astronomy.ie. Now, one thing we have every year is our annual big barbecue under the stars, a fundraiser where members who've been in the subject for a bit longer than others and have got a big telescope very kindly bring it along and let everybody look through it. This year, the wonders of the universe included Saturn with its rings almost edge on. Now, including all the volunteers, around 500 of us at the dark skies of the Wicklow Mountains on the 31st of August. Next year, it's on the 20th of September. If you forgot that, go to the events section on our website. You'll see it's already booking if you want to get tickets at the early bird rate. But we also talk in schools because we want to get young people interested in astronomy in particular, science in general, and inspiring the future has been something we've been trying to do since our 25th anniversary. The society was founded 34 years ago. We do have a huge media presence as well. We've been all over the media as usual since the last meeting. And the last meeting was, as I said, on the 9th of September, when we had Mary McIntyre, an amateur astronomer, but an avid broadcaster, writer. There's a book coming out talking about what has space done for us. And if you watch that talk, you will certainly know. She covered so many aspects of why spending money on space is a great idea. If you missed that, you may have noticed we're recording this lecture. You can get a recording or a DVD or both if you go to the website and look up astronomy.ie/DVD if you're to that. And there are lectures going back over a decade now that you see you like the look of. We can send them on to you. After that, then we had the International Space Station was in evening skies. There was a bit of a space chase, but it was mostly clouded out, unfortunately, when a new crew was sent up. That ran from the September 11th to 29th, when ISS was the brightest thing in the sky. There was nearly a record number of people on board. It won't be back in evening skies again until November, and we'll post daily predictions free on our social media, Facebook, Instagram, X, So follow that, because that's where we also predict eclipses every day. We just sent out the alert. You usually do it just before sunset. We sent it out not long ago, in the last hour, I'd say. And you'll notice there was an aurora last night. I saw it myself, got some great pictures of it. So did other people. It's the ninth aurora I've seen from Ireland this year, despite our weather. You can imagine many of them would have been, had it been clear every single night. And that's because we're near solar maximum. You can expect more aurora this year and next year and for several years to come. We talked about the aurora on Today FM, national radio, on Saturday morning. It was in the Irish Times. They interviewed us as well, and the Irish Independent. So there were a lot of people watching out for it. We thought it might come on Saturday night. In the end, it started on Sunday during the day and slowly built, unusual in that regard, until by about 10 o'clock it was visible from Ireland. And around, if you stayed up to 1 or 2 o'clock in the morning, that's when it really stormed. And it's been active today as well. And just before I came on, I checked the activity. It looks like the aurora could continue going this evening. It's not really forecast, but you never know with aurora. They can be tricky things to predict. Eclipses and other things we can do exactly to the nearest second. But aurora, a bit like they are space weather, they are really like weather. They have a mind of their own. They come. I've seen them 12 hours earlier, 12 hours later, not at all sometimes. And occasionally they appear when we don't expect them. But we'll try and predict them for you every day. So make sure you follow us on our social media. The links are at the bottom of astronomy.ie. The other thing that was in the media, of course, was the big eclipse we had. And you had to stay up till about 3 or 4 o'clock in the morning. Was it September the 18th? We were on the TV and radio talking about this. And in the end, Ireland was almost totally clear. It's probably as rare as an eclipse is. I watched it from start to finish. So we got a beautiful view of it. Loads of people sent in photographs. We're putting them in November issue. The October issue was more or less complete by then. And you'll see a souvenir issue of the eclipse, the 2024 lunar eclipse from Ireland next month. And if you missed it, there's another eclipse coming on the 14th of March next year. And the one in September last month was partial. The one in March next year is total. Will it be clear? I mean, the Irish weather, 3 out of 4 nights are totally cloudy. But we can live, all we can do is hope. So we've been very busy in the media. In fact, we got on television talking about another topic that was very popular with the media, and that was the Earth's new mini moon. Now, our own moon's over 3 million meters across, and this moon's only 10 meters across. But because it got trapped by the Earth's gravity officially for about 8 weeks, starting Sunday the 29th, was it? 29th or 30th of September, for about 8 weeks. Technically, we've got 2 moons, although one you won't see it. It's extremely faint. Into astronomy, it's below magnitude 20. It'll escape then in November, but it'll come back in January when it'll be 18th magnitude. Some amateur telescopes in Ireland could pick it up then. I'll even have a go myself. So as you can see, very busy in the media all the time. And we warned you last month and in the magazine that Mercury is making its best morning appearance. I saw it. It passed near Regulus. Got to see that as well. Jupiter was near the moon on September 23rd. I managed to get a view of that, waiting for the clouds to clear. And Mars did it 2 days later on the 25th. And these are extremely bright objects next to the moon at this stage. So hopefully you got to see all those too. They were all predicted in the magazine, and reminders were sent out in the weekly email that we send. So if you're not a member of Astronomy On, do join. The magazine's aim is aimed at kids, families, people who don't have a scientific training. So I'm sure you'll enjoy some of these naked eye wonders. So a very busy month, as you can see, this time of year, when the nights are getting dark earlier, there's lots happening. And we're delighted then for Space to welcome Dr. Mark Norris of the University of Central Lancashire. He's a senior lecturer in astronomy at the university. He specializes in research into large star clusters, but also galaxies as well. And he teaches courses on campus for the undergraduate degrees in physics with astrophysics and astrophysics degrees, as well as supervising master's research and PhD students, studying a range of topics in astrophysics. And he's chosen a very interesting topic that we've been following in pages of the magazine. This is a topic over the last decade, certainly, that's developed enormously about where the kind of atoms that are in our bodies and make up a lot of the universe, apart from what was made in the Big Bang, come from. So I'm fascinated to hear an expert tell us the very latest information on all this. knowing it includes lots of exotic objects. So thank you very much, Mark, for agreeing to give our Space Week talk. And over to you.
Thank you. I'll just try sharing my screen now and get the presentation up. That one. I'm just going to take this very brief chance to try and advertise for some students, actually, because I'm sure you've got some people who are joining here who might be interested not just in undergraduate degrees but in research degrees in astronomy. And I just want to point out that we do distance learning research degrees in astronomy, and we've been very successful in getting some really great students through astronomical societies and through organizations like yourself. So I just wanted to take that chance because there might well be a diamond in the rough watching this who thinks they don't necessarily have the right background, but you'd be surprised. I actually have an excellent master's student at the moment doing a really fascinating project, had no undergraduate degree at all, but was a senior software engineer, so had all of the prerequisites needed to do really good research work. So I just wanted to give that chance because getting a really good master's or PhD student is a great way to get some excellent research done. So anyway, I'm going to talk about our cosmic origins today, and this is something that's grown out of my own research, but also my on-campus teaching. So let's see, why is it that I'm the person to talk to you about this? Well, I got my degree and PhD at Durham in England. And after that, I went and did postdocs at the University of North Carolina at Chapel Hill and the Max Planck Institute for Astronomy. And my research in all of those places is pretty much focused on how galaxies form, and in particular, what you can learn about galaxy formation from star clusters like globular clusters, ultra-compact dwarfs. And one of the key insights you can gain from those objects is their chemical composition. You find things that are more chemically complex later in the universe generally, but also in the densest environments in the universe. And so chemical composition, chemical complexity is a sign of how star formation has progressed in a particular body. Right now, I continue to do that work. I'm, like you said, senior lecturer at UCLan. I also run, I think director is probably a bit too grand a term. I manage the Alston and Moore Park observatories. We're quite fortunate here that we have probably two of the most powerful telescopes in the United Kingdom at the moment, including a 70 centimeter plane wave robotic telescope. So I'll just skip that because it's not really relevant. So getting on to the talk at hand. If we're in person, I would be asking this as a question for the audience. So you can play along at home. Around 99% of the human body by mass is made up of just 6 elements. And in fact, 65% of your body by mass is made up of a single element. Now, I've asked this question, what is that element, to a lot of different groups, and I think I've only got the right answer once or twice. So have a think in your mind. I won't put you on the spot, but I will tell you that the most common element in your body is oxygen. And when you think about it that a little bit, it makes perfect sense. You're mostly water. And of course, most of the mass of water is in the oxygen because it weighs 16 atomic mass units, whereas the two hydrogens only weigh 2 atomic mass units. So the majority of your body, the overwhelming majority really of your body, is oxygen. The next most common element is carbon. And carbon effectively is the bag that's holding that water in. Followed by hydrogen. So the water, and also, of course, in the fats and things like that, that also make up your body. And then after that, you're really starting to get down to trace elements. You've got some nitrogen, you've got some calcium in your bones, phosphorus, and that's the top 6. Everything else that's in your body is less than 1%. Now, there are over 50 detectable elements that are found in the human body. And they form or basically described as in being in one of three groups. Contaminants, so they are things like titanium that, as far as we can tell, are not used in your body in any way. They've just sort of made their way into your body, but they neither harm nor hurt you, so they just sort of stick around. Then you have your poisons like arsenic. They get into the body and they do actively harm you. So obviously we're talking about trace amounts here, otherwise you wouldn't be around worrying about the amount of poison in you. And then you have the essential trace elements, things like iron. So iron, of course, is essential to humans because it forms a key part of hemoglobin, which is what's used to transport oxygen around the body. So people have looked at this in detail, and they think that around 20 to 25 of the periodic table elements are essential for humans. There are something like 20 that are definitely known to be essential, and there's another 5 or 6 which are suspected, but no one's been able to demonstrate conclusively, because obviously essentially any test to prove this would be completely unethical. So this, like I said, 20, 25-ish elements that we think are essential. And then the vast bulk of the periodic table, the remaining 80 or 90 or so elements, apparently are not necessary for at least human life. Now, all of those elements were created in space. And so explaining where and in what quantities has been one of the key drivers, really, of large areas of astrophysics for, well, almost a century now, certainly since the discovery of radioactivity and in particular fusion in the 1940s. It was realized that essentially all of those elements were probably created in space somewhere. So I always love this Douglas Adams quote: "In the beginning, the universe was created." This made a lot of people angry and has widely been regarded as a bad move. So if we go to the beginning, we have, of course, the Big Bang. Picture not representative. Of course, there's no way to really draw a good picture of what the Big Bang looked like, but that is the beginning of the universe. And as we know now, it occurred about 13.7 billion years ago. That is the origin of everything. Now, we're able, and it still astounds me that we're able to do this, but we are able to work out that before the universe was 10 to the power minus 32 seconds old, in other words, 0.32 zeros and a 1 seconds old, it went through a very rapid period of exponential growth. And this period we call inflation. This period is very important for our story because it takes these tiny cosmic fluctuations that occur within essentially every cubic millimeter of space, within atoms, outside of atoms, these quantum fluctuations that are always occurring. It takes them, and normally in the universe, as it is now, those fluctuations will make a pair of particles appear, and then those particles will cancel out. Another pair of particles will pop up over here and then cancel out, and the net effect is essentially negligible. But in the early universe, inflation acts so rapidly that those little fluctuations get grabbed by inflation and then get expanded up to macroscopic scales. And so features that started out as maybe 10 to the minus 15 of a meter in size get grabbed by inflation and then inflated up such that today they could be tens or hundreds of millions of light years across. And for our story, that's essential because it is those fluctuations that provide the initial structure to the universe, without which the universe would just be so smooth initially that we wouldn't have had any collapse occur even today. We would still be in a situation where essentially the universe was just the raw hydrogen and helium spread out equally. So inflation takes those quantum fluctuations and blows them to macroscopic scales. And it does that for all scales in between. That's one of the important things. It doesn't just make structure that is the size of superclusters of galaxies, it also makes structure that's the size of clusters of galaxies and of galaxies and of sub-galaxies and of potentially even star-sized structures, although they would be washed out, we now know. So that sets the seed of all of the structure that we subsequently have in the universe. So the next thing in our story that's important for us is that was 10 to the minus 32 of a second after the Big Bang. We're now into the period of fractions of a second to a few seconds after the Big Bang. And within the first second or so of the Big Bang, the universe produces protons, neutrons, and electrons. If I knew how or why, I would have a Nobel Prize. I don't. We just know that it does and how many it produces. And we actually know why it produces the ratio it does. It produces slightly, well, 6 protons for every neutron that it makes. And that's because protons are slightly lighter in mass than neutrons and therefore are easier to make. So it just makes more protons. So within a second or so, we have 6 protons and for every 1 neutron in a plasma in the universe. Now, the problem is at that point, the universe is very hot. It's so hot that those protons and neutrons can't actually couple up and make anything more complex. The temperature just breaks them apart constantly. So whilst the universe is sort of expanding now at its normal rate, the temperature is dropping, the density is dropping, and eventually it'll reach a temperature and density where you can get the basic fusion reactions to start to occur. So a proton will hook up with a neutron to form deuterium. It's the first step. That, however, takes about 10 minutes. And if you takes about 10, 15, 20 minutes, that sort of time frame. The problem you have is that the neutron will decay with a half-life of about 10 minutes as well. So as you're waiting for the universe to cool down, the neutrons are actually decaying, and they decay into protons. So your 6-to-1 ratio gets adjusted while you're waiting for the universe to cool down enough that you can do anything interesting. And so by the time that's finished, about 3 minutes in, the temperature reaches cool enough point that you can start fusion reactions. You've actually got 7 protons for every 1 neutron. And then things get really exciting very quickly. So between 3 and 20 minutes after the Big Bang, the entire universe becomes essentially a fusion reactor. So this is actually a view inside, I think it's the JET fusion reactor, but you're seeing a fusion reaction occurring in that plasma there. So for between 3 and 20 minutes after the Big Bang, essentially the entire universe has a density that's roughly similar to the density of air in the room and a temperature of hundreds of billions down, falling down to tens of millions of degrees. And those conditions are just right for it to become essentially a giant fusion reactor. And so this chart shows the overall reactions, but the basic takeaway point is just that every single neutron ends up hooking up with a proton and then forming things like deuterium, so heavy hydrogen, or even tritium. So that's 2 neutrons, 1 proton. It'll then rapidly run around the reactions until most of it, almost all of it, gets soaked up and becomes helium-3 or helium-4. So helium-3 is 2 protons, 1 neutron. Helium-4 is, of course, 2 protons, 2 neutrons. And so we end up at the end of Big Bang nuclear synthesis 20 minutes after the Big Bang. So that's literally 20 minutes after the Big Bang. And we have ended up with a universe that's basically 75% hydrogen, 25% helium by mass. And then you get very small amounts of deuterium, helium-3, and lithium as well. And so that ratio, that 75% hydrogen, 25% helium, that's just a direct result of the 7-to-1 or 14-to-2 ratio of protons to neutrons that we had originally. And so just because of basic atomic physics and the ratio of the mass of proton and neutron and the half-life of the neutron, we end up locked in that the universe is going to produce 75% hydrogen, 25% helium. That is it. That's the raw material. After that, everything else in the periodic table is produced, in stars or in the things that stars become. So all of that hydrogen that is in our bodies, pretty much you can count that 100% of it comes from the Big Bang. So if you remember, that was something like 10% of your body. 10% of it's just come unmodified, essentially, from the Big Bang. Now, that was 20 minutes after the Big Bang. The fluctuations that I talked about, the quantum mechanical fluctuations that got blown up to enormous scale, well, we get a picture of them about 380,000 years later. After 380,000 years, the universe has cooled sufficiently that you get a situation where the free electrons in the plasma can attach themselves to atoms. And that's a really important moment in the history of the universe, because when the universe was a plasma, so before 380,000 years, it's opaque. It's like a cloud, because a light particle, a photon, will interact with any free electron it comes across. And so a photon trying to travel to you will be constantly jostled by the electrons in the plasma, and it will have its direction constantly changed, which means that you can't see in a straight line and you get a fuzz, a glow. Once the electrons attach themselves and you form to protons and to nuclei and you form neutral atoms, then the photons can start to travel in straight lines, because now they can only interact with an atom if that photon has just the right energy to move an electron from one energy level to another. If it doesn't, it just basically passes by in most cases. So what you see in this picture is essentially the moment, which isn't a moment, it's, thousands of years in time, but you're seeing the moment where the radiation, the light, decouples from the matter and streams away into the universe, forming the cosmic microwave background, the leftover heat of the Big Bang. This is that heat being released from being locked in with the material. And what's important is you can see it is not uniform. It is a series of bumps and wiggles and hot and cold spots. And those hot and cold spots, they were produced by the quantum fluctuations we talked about earlier. And the sense of scale here is very important. The difference between a hot spot and a cold spot is something like 1 part in 100,000. So the hot spots have 100,001, and the cold spots have 100,000. And what that means in practice is the hot spots end up with 1 part in 100,000 more atoms than the cold spots next to them. And that is enough. That is enough for us to build a universe out of it. So what we will see in a little while is that because the hot spots have 1 part in 100,000 more than the cold spots, they have more mass. They therefore have more gravity, which means they can attract even more mass. So they get even more gravity. And then they will have a runaway process where they just get bigger and bigger. But for our story, this is where the universe goes dark. It goes dark, which we call the Dark Ages. The universe looks like this because the glow of the Big Bang is now being redshifted by the expansion of space. So it's moved out of the optical regime. You can't see it with your eyes anymore. It's infrared. And there are no stars or black holes or anything else producing light at this point. The universe is just completely dark. But in the dark, the matter is beginning to clump. Gravity is beginning to pull things together. And so if we look at the simulation, it shows a simulation of galaxy formation, and the dark smudges you see, they are the regions that have 1 part in 100,000 more than the lighter blue regions. And then if we just let gravity do its thing, over time, gravity will pull that mass together such that the regions with more mass initially get even more, and they get denser and denser. And importantly, the regions which had less material, the underdense regions, they will lose their material. They will become more and more underdense. They will become what we call voids. And so you can see here we've zoomed in a scene on something that will end up like a Milky Way disk galaxy. And you can see this process is quite chaotic. The galaxy, the proto-galaxy at the center of the deepest part of this gravitational potential well, pulls in lots of other little galaxies, and it eats them in order to get more gas to grow. So each of those smudges you see around the main galaxy, they're all dwarf galaxies being eaten by the bigger galaxy. Now, what's happening in that galaxy, if you zoom in, is a very similar process. So if you zoom right into a single star forming region, it will look very similar. You will find that the gas that is accumulated in one of those galaxies will collapse down under its own gravity, and the regions that had a slightly more density, they will collapse away and get denser and denser. And eventually they will form these stars in the center of it. So this is very similar to what happens to galaxies on the larger scale. The only real difference between the two is that the galaxies, in the galaxy's case, their collapse is governed by dark matter. It's the dark matter that has the dominant amount of gravity and does most of the dragging of material together. In this case, it's just pure gas. There's not much dark matter inside of galaxies affecting this process. So it's just the pure gravity of the gas itself pulling it down. The other difference is the time scale. For a galaxy, your period of star formation, your period of growth can be hundreds of millions or billions of years. For a single star forming knot, it can be hundreds of thousands to a few million years at most. So at the end, the simulation ends, and you can see you have formed a star cluster there. And that looks very similar to some of the pictures of forming star clusters that are coming out of instruments like the JWST. You can see there's a central star forming cluster there, and what's actually happening is the light from that cluster is pushing the gas away to unveil the cluster that's formed at the center. So this is the process where the star formation is being cut off because the light of the cluster is beginning to push the gas away. Now, stars. Stars are going to do a lot of the work that we need to explain where the chemical elements come from. So we do have to understand the basics of what a star is. And as I always say to my students, a star is just a temporary truce between the inward force of gravity trying to compress the star down and the outward restoring force caused by the pressure of that gas. So a star, as you know, I'm sure, produces the bulk of its energy by fusing hydrogen to helium in its core. That heats up the core, and that produces pressure, and then the pressure holds the star up. I say it's a temporary truce because, of course, eventually the star will run out of fuel. And when it runs out of fuel, the gravity is still there. So the gravity will always win this fight. It's only a question of how long. And so almost everything about a star is controlled by the mass it has at birth. There's only a couple of other parameters that make much of a difference to a star, one of which is the chemical composition. But by far the most important is its initial mass. Now, as I said, all stars spend most of their lives fusing 4 hydrogen atoms to make 1 helium nucleus. And this plot shows one of the most important plots in astrophysics. It's called the Hertzsprung-Russell diagram, the color magnitude diagram. There's a lot of different names. But what it's showing in this form is the luminosity of the star in solar units against the surface temperature of the star in just Kelvin. And so by definition, the sun has 1 solar luminosity, and it has a surface temperature of nearly 6,000 Kelvin. And along this line, this line known as the main sequence, this is where stars fusing hydrogen to helium live, all the way along the black line that you can see. The interesting thing is that the relationship between the mass of a star and the luminosity is not linear. So if I double the mass of a star, you can see I did not double the luminosity. So if we're going from 1 solar mass to 2 solar masses, does not make a star that's twice as bright. It makes a star that's 30 or 40 times as bright. So a star that's actually 10 times heavier than the sun is 3,200 times brighter. Much, much brighter. And for our story, that has really important implications. The most important implication is that star must live a much shorter life because it's only got 10 times more fuel, but it's burning it 3,200 times faster. And that's a simple result of the fact that a heavier star has more gravity. It therefore has to produce more energy more rapidly to be able to hold its own weight up. So in that example, a 10 solar mass star will only live 1/320th as long as the sun. So if we look at stellar lifetimes, a 100 solar mass star will last about 1 million years. A 10 solar mass star will last about 31 million years. The sun will last about 10 billion years. And a lowest mass star that you can possibly get, which is about 8% of the mass of the sun, they'll actually last about 10 trillion years. So they'll last another 1,000 times longer than the sun. For our story, that's important because it means that any star that's less massive than about 0.8 or 0.9 times the mass of the sun, none of them has ever died in the history of the universe. The universe just hasn't been around long enough for stars like that to have died. They're all still just burning on the main sequence. So anything down here, every single one of them is still alive now. Anything above there, some of them will have died, some of them will still be alive. Just depends how long ago they were formed. So as I said, all stars spend most of their lives fusing hydrogen to helium. And they do that in their core. Something like the sun, it's only ever the inner 10% of the mass of the sun that gets fused during this stage. The way they do that, they can do it in one of two ways. They can do it using something called the proton-proton chain, which is what happens in the sun. And that is literally just you have 2 hydrogens come together and one of them spontaneously decides, I don't want to be a proton anymore. I'll turn into a neutron. And that gives you a deuterium. That will then merge with another hydrogen later, and that will give you helium-3. And then the same thing happens in another chain, and the 2 helium-3s come together and produce a helium-4 and spit out 2 hydrogens. Importantly, if you look at the mass that comes out, if you look at the mass of helium-4 and the mass of 4 hydrogens, the mass of helium-4 is less than the mass of 4 hydrogens, and the difference between the two, that is the energy that's released. And it's quite a lot. It's like 0.7% of the rest mass of the particle. So, quite a lot of energy. The CNO cycle, well, that can only really, couldn't have happened for the first stars because it's a catalytic cycle. So basically you start off with something like carbon-12, you add a hydrogen to it, get nitrogen-13, that then decays into carbon-13, you add another hydrogen, you get nitrogen-14, add another hydrogen, you get oxygen-15, that decays to nitrogen-15, you then add another hydrogen, and what you get back is carbon-12 plus a helium. So it's catalytic because you get your carbon-12 back again, but you also get out a helium-4. Overall, though, the net reaction here is exactly the same as in the PP chain, and it releases exactly the same amount of energy. So it doesn't really matter which one you're doing, but stars do use these two different methods. It just depends on the temperature of the star's core. So in stars slightly more massive than the sun, it's higher temperature, and this chain is favored. But for our story, importantly, this does nothing to increase the chemical complexity of the universe, because you get back what you put in. The only thing you change is you've changed some hydrogen into helium. So that's saying that the PP chain works for low mass stars, and then the CNO cycle happens for high mass stars or higher mass stars. So this is the overall reaction. 4 protons go to 1 helium plus 2 neutrinos and 26.7 mega electron volts of energy per reaction, which is quite a lot for atomic physics. The helium builds up in the core of the star, though, as ash. And we call it ash because it's inert. At least initially, the star is not hot enough to be able to do anything with that helium. It just sits there and gets heavier and heavier, because as the fusion proceeds around it, all of the helium that's produced will sort of settle down and add to that helium core that's inert. Now, in all but the tiniest stars, that inert helium will build up and collapse under its own weight until eventually it reaches a high enough temperature that you can begin to fuse helium. And that's a process called the triple alpha process. So you take 2 heliums, turn them into beryllium, you add another helium, and you end up with carbon-12. And this fact is one of the reasons why the lightest elements in the periodic table after hydrogen and helium are extremely rare. Lithium, beryllium, and boron are underabundant. They're very rare in the universe because they're not made in stars. You go straight from helium to carbon, jumping everything in between. And so that explains why those elements are just very rare. Now, in stars less massive than 8 solar masses, the helium burning will eventually produce carbon ash. And for stars less massive than 8 solar masses, that's basically the end. They never get hot enough to do anything with the carbon. So you end up with just a carbon core that is inert. And so that's what will happen to the sun. The sun, this is essentially a track of the lifespan of a 1 solar mass star, and the sun is here. It will eventually start doing helium burning and all that sort of stuff, and at that point it will become a red giant, but that will be all the sun will do. After that phase, once it's built the core, that carbon core, it will go through a planetary nebulae phase where the core essentially pushes off the outer layers of the star, and that will leave behind at the center a white dwarf. And that white dwarf will basically be pure carbon. And, you know, depending on the mass of the star, it could be, 20% of the mass of the sun up to, almost 1.4 times the mass of the sun, as we'll see. So that is the eventual fate of a star like the sun. 90% or so of its mass will be kicked off into space, and you will get a small cinder left behind. And that cinder will glow with the residual heat and the gravitational collapse energy that it has left for billions of years. Because remember, this was the core of a star. It was originally hundreds of millions of degrees. It weighs a huge amount, so it retains that heat, and then it radiates it away, and you get a planetary nebula because the surface of that star will, actually increase to 100,000 Kelvin perhaps, which produces ultraviolet light that ionizes the gas cloud that it's just pushed off around it. But eventually it will essentially just cool down and disappear if it's a star like the sun, which is on its own. So you get a white dwarf. The density there, when it's done, is about 1 billion kilograms per meter cubed. So that is gravity pulling the material down and down and down until the point where the only thing that can hold it up anymore is the repulsion between the electrons in the atoms. Except it's not the usual electronic repulsion that we're all used to in electromagnetism. It's the quantum mechanical repulsion caused by trying to put two electrons together. So this stuff is much, much denser than normal matter. You can see rock is 3,500 kilograms per meter cubed. That is supported by electrons just repelling with electromagnetism. You get down up to 1 billion kilograms per meter cubed if the electrons are now repelling each other using quantum mechanics instead. During the death throes, though, that star can dredge up some carbon and nitrogen, and it can synthesize some carbon and nitrogen in the ejecta. And we see it in these beautiful planetary nebulae. Those dark regions, they are basically dust. If you look at them chemically, they look a lot like cigarette smoke. For the similar size, you get the same polycyclic aromatic hydrocarbon kind of chains forming in that environment. And so much of the carbon, or some of the carbon and nitrogen in our bodies, is produced during this phase of the death of sort of mid-sized stars. So if we look at our periodic table, we actually get the majority of the carbon and nitrogen of our bodies through this process. And then some unusual ones like molybdenum and tin is also produced in the same way. In stars greater than 8 solar masses, well, they are heavy enough such that they can continue to burn heavier and heavier and heavier elements. And you end up with this, what's known as characteristic onion skin pattern for a star, where it has different shells fusing different elements. So at the very center, you will have iron ash, which is the result of burning silicon into iron. And then above that, you'll have silicon fusion, magnesium fusion, neon fusion, oxygen fusion, carbon, helium, and again, eventually the hydrogen fusion that you had as well. Stars of greater than 11 solar masses, there's a bit of a debate about where exactly you can burn all the way to iron. It depends, again, like I said, on things like the metallicity and structure of the star, but it's somewhere between about 8 and 11 solar masses. You can burn all the way up to iron. And if anyone wants to ask me at the end, ask me again, because that's not technically true. And it's an interesting reason why it's not technically iron that gets made, but we'll brush over that for now. Now, once you get to an iron core, you are in real trouble, because the period that a star has to burn each of these different elements gets shorter and shorter and shorter, because each subsequent reaction gives out less and less energy and required more and more of the previous steps to get to it. So by the time you get to burning iron, the star's lifetime will be measured in days. And what will eventually happen is it will start having these massive winds, because it becomes very unstable, because the fusion reactions become very sensitive to small changes in the temperature that can lead to it becoming really unstable and throwing out the outer layers. But the key point is just the iron keeps building up and building up and building up until eventually the iron that's building up becomes heavier than the electron degeneracy pressure can support anymore. So why do we stop at iron? Well, we stop at iron because of a simple or weird quirk of nuclear physics. This plot just shows you the binding energy. In other words, the energy that can sort of be released by fusing elements together, or alternatively by breaking them apart. And what we see is that around iron, we reach a maximum in the binding energy per nucleon. And that means that if I start with a light element and build up, I can release energy all the way up to iron. But once I get to iron, if I want to go and keep making things bigger, I actually now have to start putting energy in. And if I'm putting energy in, that can't be being used to produce kinetic energy and it can't be being used therefore to produce pressure, and it can't be therefore being used to support the star anymore. So once you make iron, that's it. You can't fuse any higher without injecting energy, in which case the star is doomed. Similar process happens with nuclear fission. If you start with uranium, you will get energy out as you split uranium apart, all these elements apart, until you get to iron as well. So overall, just a quirk of nature. Once you reach iron, that's it. Game over for the star. And so the iron core, because it can't be supported by electron degeneracy pressure anymore, it will collapse. And it will collapse at almost free fall speed. It will go from being, greater than 1.4 times the mass of the Earth, a mass of the sun, sorry, and about the size of the Earth. And it will collapse down to being about 10 kilometers across. And it'll do that in a fraction of a second. It will collapse all the way down until you've crammed every available electron onto every available proton. So every nucleon in the star, or at least in the core, is converted into a neutron. And then it will eventually be stopped from collapsing further by the fact that neutrons don't like being jammed together either. So you get neutron degeneracy pressure. That core then just stops, but then all of the material that was around it is still falling onto it, and falling onto it at an appreciable fraction of the speed of light. It then hits that star or the core and bounces off the neutron star into space, whilst being bathed in an incredible flux of neutrons, which attach themselves to all of the material that was already there. And so that process, a type 2 supernova, will throw a lot of material into space with a lot of neutrons around at very high energy, and that will lead to lots of fusion reactions. And we'll get an example of this if we're lucky in our lifetime, because the star Betelgeuse, the big red star of Orion, is a massive star that will go supernova at some point. And when it does happen, it will be bright enough that you will see it during the day for several weeks. So, I'm always torn on this one, because I'd love to see it, but also once it fades away, Orion will never look the same again. So that's a type 2 supernova. The resulting explosion blasts those outer layers into space. And those outer layers were things like silicon, magnesium, neon, oxygen, carbon, helium, and hydrogen. And so you get all of those out. But then you also get loads of new elements, because the neutrons start being attached to those elements and then decaying into different elements along the way. So if we look at it, those exploding massive stars, those type 2 supernova, they explain basically 100% of the magnesium, the oxygen, the fluorine, that kind of thing, and large fractions of the other elements of the human body. So you already see that we're getting a strange mix. The majority of your body by mass was blasted out of type 2 supernova, but large fractions of what holds that mass in was made in just dying average stars like the sun. And of course, all of the hydrogen was made in the Big Bang. The other type of supernova we have is what we call a type 1a supernova. That forms a completely different way, and it will never occur in a star system like ours. For a type 1a supernova, what you need is a binary star system. So what happens there is that if you have a binary star system, one of the stars is almost inevitably going to be slightly more massive than the other. That means it will live its life faster and it will die faster. And if that star was one that would turn into a white dwarf, well, that's what it'll do. It'll live its life, it'll go through its red giant phase, it'll have its planetary nebula, and it'll leave behind a white dwarf. During that process, it may even transfer some of its mass to the companion. But anyway, it leaves behind a white dwarf, and that white dwarf starts or continues to just orbit around the second star. And of course, as time goes on, eventually that second star will reach the end of its life. So that's what that might look like in the planetary nebula phase. I'm just going to zoom back in. There we go. Now the second star has evolved and is becoming a red giant, and the white dwarf is continuing to go around it. And of course, when the second star becomes a red giant, the strong gravity of the white dwarf will be able to steal material from the companion. So that's what you're going to see in a second. It's now a red dwarf, and the gas is going to go from there onto the white dwarf. And so we see this in recurrent nova all the time. They get, and I want to be very clear that 1.44 number there is wrong. It's about, the number you actually have is about 1.4 solar masses. What happens, and this is different to what a lot of you might have heard, because we've learned a lot in the last 20 years, and the textbooks or so haven't really caught up yet. But what really happens is that as the material, I'll get it going again. As the material goes onto the white dwarf, you eventually get this mass of about 1.4 solar masses, and at that point, the white dwarf, which is mostly carbon, it just gets to just the right conditions where a small fusion reaction somewhere will happen. The carbon will fuse with another bit of carbon. That will release a bit of energy. And that bit of energy will then trigger a bunch more fusion reactions, which therefore trigger a bunch more fusion reactions. And in the space of a few seconds, the entire white dwarf of pure carbon basically fuses itself all the way up to iron. So the white dwarf, in a second or two, turns itself into a giant thermonuclear bomb with a runaway reaction. And the key point is that will leave nothing behind. That star will completely blow itself to pieces. And in the process, it produces, it converts about half its own mass into iron. And you can see that what it naturally does is produce a lot of iron peak elements, the elements that are near iron in the periodic table. So like I said, if it was a 1.4 solar mass type 1a, which they basically all are, about 0.7 solar masses of that comes out just in iron. So it produces most of the iron in the universe. It's ironic, most of the iron in the universe is created in massive type 2 supernova, massive stars, sorry, but none of that iron ever leaves those stars, at least the stuff in the core, because that is the material that collapses down and becomes a neutron star. Almost essentially all the iron that we have out in the universe comes from these lower mass stars, these type 1As going supernova. So it's a bit of a quirk of nature. There's a lot of iron produced that never gets out of the core of a star. Okay, so that's most of the periodic table, but or at least most of the elements that we're interested in. But you can see that we're still missing a few, fractions from molybdenum, tin, and all of the iodine. And that is something that we only learned about in the last few years, really. And that comes about because of merging neutron stars. So remember, you form a neutron star during a supernova, a type 2 supernova, one of these massive stars exploding. If you have a binary star system which has two stars that are more massive than 8 solar masses, well, eventually what you will get is 2 neutron stars, because they will both go type 2 supernova. They will both leave neutron stars behind. The neutron stars will then orbit each other, and because they are so massive, they are warping space-time itself. And that leads them to spiral in, because they produce gravitational waves which radiate away their angular momentum, their kinetic energy, and that allows them to spiral in faster and faster and faster until they hit each other. Now, that is a fascinating process, because we had seen merging black holes before, but merging black holes are not particularly exciting, because what you get out of 2 black holes merging is a bigger black hole. You don't produce anything that will produce a signal in the optical or the infrared. You just produce a gravitational wave signal. But merging neutron stars, well, neutron stars are physical things. They're made of neutrons. When they hit each other, they will get hot, material will get knocked off, it will glow, and therefore you expect you'll see a signal of that. And rather amazingly, in 2017, we did. So in 2017, the LIGO and Virgo gravitational wave detectors detected a gravitational wave signal that was consistent with two neutron stars merging. That got everyone very excited, and thankfully, because we had three separate detections at different detectors around the world, you could triangulate where on the sky that signal came from. And then basically every optical telescope in the world starts looking in that patch of sky to see if we could see the signal of merging neutron stars. And we got incredibly lucky because it was detected almost immediately. And through pure dumb luck, a few months before, the Hubble Space Telescope had been looking at this particular galaxy. And then the day after the gravitational wave signal came in, someone was looking with a ground-based telescope, just checking out every big galaxy in the region where they knew the gravitational wave signal came from. And they saw a bright spot that wasn't there before. Now, that will get you excited, but it doesn't necessarily mean it's the signal. It could have been just a normal run-of-the-mill supernova, type 1a or type 2. But what was really fascinating about this thing was it did everything wrong for a supernova. One thing was it was red. Supernova are blue, very blue. The other thing that was odd about it was it faded really quickly. Supernova do the opposite. When they go off, they actually brighten for the first 15 days. That's because much of the energy of a supernova actually comes from radioactive fission in the products that are made in the cloud. So that fission takes a few weeks to occur, and that actually bumps the temperature of the exploding gas cloud up for a few weeks, making the supernova brighter and brighter. This one didn't. It started bright and faded away, and it was the wrong color the whole time. And then finally, people were able, because it was just about bright enough, to get a spectrum of it. And what they found was entirely consistent with this picture where two neutrons stars hit each other. They found Earth masses of elements like platinum, rare earth metals, that kind of thing. Things that we hadn't seen in any other spectrum before. And the explanation for this is really crazy. You smash two neutron stars together at an appreciable fraction of the speed of light, and what you end up doing is knocking things off the neutron star, which are, Earth mass the size of Everest, composed completely of pure neutrons. And as they fly away into space, the neutrons begin to decay into protons, and they keep decaying until the things break up into stable atoms. So you get the right ratio of protons to neutrons. And in practice, that means you end up, being able to form elements all the way up to uranium and plutonium even. And so from the signals people recorded in that event, we're able to explain that molybdenum, tin, and iodine, most of the iodine certainly comes from merging neutron stars. Completely crazy that we now know that. And so we're able now to give a really fascinating plot version of the periodic table where we can explain where basically all of those elements come from. And you'll notice there are a few fun ones like technetium down here at 43 and whatever that is over there. And then these heavier ones, they're fun because they do not have any stable isotopes. They just, in nature, they have isotopes that only last, maximum of millions of years or something in some cases. So even if you synthesize them in space, which you will, they never last long enough for us ever to detect them in space. We basically only know about them because we can make them in laboratories. Of course, these ones down here last, tiny fractions of a second. So that's the periodic table now as understood astrophysically. And the last question then is how you get those elements from the interstellar medium to a planet like the Earth. And the answer is, well, galaxies like the Milky Way are just excellent recycling machines. Those spiral arms of the Milky Way essentially sweep up all of that gas and dust ejected through all of those different processes, concentrated in the spiral arms where it gets dense enough that it can form stars, as we've seen before. And then as the stars collapse, they naturally collapse to form disks because they're conserving angular momentum. And then out of the disk, I forgot there was noise on that one. As the as the disk goes around the star, the planets will again begin to fragment out of the disk material and again go through their own gravitational collapse, at which point they will grab material from that solar nebula, which will include all of those elements that we've seen before. Now, repeated mergers then grow the initial seeds planets over time and can lead to new materials being brought in. One of the complications of planet formation is just the fact that what materials you will get will depend on how close you are to your star, because as the planet's forming, it depends basically on the melting point of the material, whether or not it can congeal and form, a solid body at that radius, or whether or not you have to, move it further out into the solar system. That explains why we have rocky planets on the inner parts of the solar system and gas and ice giants in the outer part. And so the amount of element present on Earth is very different to what is found in the human body, obviously, but it's also very different to the solar system as a whole. So if you look at Earth, the majority of the Earth is made up of things like oxygen and silicon and calcium and iron. But if you look at the solar system as a whole, by far the most common element of course, is hydrogen, still in the sun. So this is the distribution of elements found in the sun. And you can see what I said before. You've got a lot of hydrogen and helium made in the Big Bang, and then very little lithium, beryllium, and boron, because all of the stars just go hydrogen to helium, helium straight to carbon. So they never really synthesize any of this down here. And so, conclusions. The elements that make up our body are the result of billions of years of chemical enrichment of the universe, and that's done by many, many generations of stars, many supernova, lots of merging neutron stars, all mixed together. You can be basically sure that 100% of your oxygen in your body came from a type 2 supernova, or several of them, before the Earth formed. For carbon, most of that comes from dying stars, but some comes from type 2 supernova. Hydrogen's 100% from the Big Bang. Nitrogen is dying stars and type 2 supernova. Calcium, a bit of both type of supernova. Phosphorus, a bit of both. And iron, if that was on there, that would be almost all type 1a supernova. So to be here, as amazing as we already, think we are, it's just incredible to think about all of the things that had to happen in space, in the right places, at the right time, to get the raw materials we need to create life on Earth. And it's one of the great questions about how common that set of events would be, and whether or not it can be replicated elsewhere in the universe. So almost all of the chemical enrichment has been done by massive stars. But one of the really crazy facts that it still blows my mind is that 97% of all the stars ever born are still alive today, because the vast majority of stars are low mass stars. So only the most massive 3% actually have died, and they are the ones that have done basically all of that work enriching the universe. So the earliest generation of stars would not have formed planets because they had no heavy elements to form rocky planets or the cores of gas giants. Chemical complexity increases over time because you've had more chance for more supernova, more merging neutron stars. But it increases fastest for the biggest galaxies. And that means the most massive galaxies would have been able to potentially form planets and life billions and billions of years before something like the Milky Way would have been able to. So that's pretty much my talk. I've just put on the screen a picture of our observatory as seen from above. Does anyone have any questions?
Fantastic, Mark. Thank you very much indeed. That's the best explanation of the Big Bang and star formation I've seen in my life. You filled in lots of gaps for me and brought it right up to date with the neutron stars. I thought black holes did produce some elements, but they don't, no? Black hole merger.
No, not really. Certainly once you've got a black hole, if you merge it with anything else, that stuff is lost to the universe. We literally think of them as sinks, sink particles. Once you're in a black hole, you're never coming out again. They can produce trace amounts of material, I'm sure. When, say, a jet from the black hole, say, irradiates something around it, but that's very much a negligible amount of material.
Well, look, I don't want to hog the question answers. If people have questions, you can type them into the chat box. You can just mute unmute your microphone and ask out loud. Very rarely a lot of competition for that. But while you're thinking up your question or typing into the chat box, just repeating what Mark said about a future distance learning course. Our own evening classes are very much aimed at beginners, running on 22nd of October. And people often ask us then if they want to take it even more seriously, where to go to. And we do say the universities now do online classes. So do check out
we've been doing it for 30 something years now, I think, about 30 years. The undergraduate side. The postgraduate side grew out of the undergraduates because one of the things we get is that our online distance learning students who come from all over the world, they're usually very accomplished people. They've had other careers, they're smart people, they're driven, and they'd get to the end of their degree and they'd kind of go, oh, what can I do now? I've enjoyed that. So we started offering the opportunity to do research degrees, and just been blown away by how good they are. I mean, we've had quite a few now doing a master's and PhD. My last master's distance learning student, who was a mature student, did a master's with me and then moved his entire family to the US to do a PhD at a US university, in his 50s. So he really got bitten by the bug.
Well, maybe we'll have to put a health warning on the classes.
Well, apparently the family are all delighted. They're living the dream, apparently. I see one question there I can answer.
Before you do, Mark, before you answer, just to tell people, I'm going to tell everybody about the big comet that's coming in the next couple of weeks. So do stay tuned for that. And I forgot to mention the TV spot we did about the Earth's mini moon. That's on our YouTube channel. You'll see the link to YouTube at the bottom of astronomy.ie, the website there, if you want to watch that. Only about 10 minutes long. So do stay tuned for the Q&A and then for the quick Sky Diary after Mark takes a few more questions. So if you want to read it out, Mark, go ahead.
Yeah, so Tony asks, how does light push gas away? So that is just because light doesn't have mass, but it does have momentum. And so if light hits something, it does impart a force on it, does provide pressure. And you can see that most obviously in the example we're just talking about there, a comet. If you look at a comet, its tail always points away from the sun. Okay, and it's pointing away from the sun because the pressure of the light from the sun pushes the material away behind the comet. And so that's really all it comes down to, is that light, it doesn't have mass, but it definitely has momentum. And you also see that in the idea of a solar sail. I don't know if you're familiar with that, but there are missions that have tested this, but you can put a very thin film in space and use light pressure to push a spacecraft potentially to reasonably high speeds. In fact, the Breakthrough Listener, or whoever it is, the Breakthrough Starshot project, which is this project to try and get a robot spacecraft to Alpha Centauri. I think it's Alpha Centauri or Proxima Centauri. Their plan is to use essentially little solar panels that they use a laser to accelerate to high speed. But it's the same idea. It's just light pushing on material.
So I have a question. How large does the mass of a star have to be to go supernova as opposed to a red or white dwarf?
Well, they'll go through, it's a bit complicated, but they'll go through, all stars will go through an equivalent to a red dwarf stage. Okay, but they might not be red. If they're very massive, they do a thing called a blue loop. They go back and forward at basically the same luminosity. The red dwarfs are the ones where they're more like the sun and they sort of go up and they get brighter, but stay at basically red color. The short answer is it's that 8 solar masses or so dividing line. If you're above 8 solar masses, you're going to go boom. If you're less than 8 solar masses, you'll end up as a white dwarf. And then the only question is how massive the left behind white dwarf is. So if you're 8 solar masses, it's going to be very close to that 1.4 solar mass limit, what you leave behind. And if you're obviously a solar mass star of 1 solar mass, then your white dwarf's going to be a fraction of a solar mass. I forget what the number is, 20 or 40%, something like that.
Great. Well, I think that's the questions asked. I'm sure people can contact you, Mark, at the university.
Yeah, absolutely. Yeah.
Your email is on the university's website, easy to find.
Oh, yes, it is. Yeah. And I'm being asked, am I speaking inside a UFO? This is our planetarium at our observatory.
Excellent.
So it's a good job I wasn't
planetarium. We're so jealous.
Sounds very strange. So yeah, it's
okay,
great
Mark,
teaching. Well, look,
I don't think there's any more questions there. Lots of thanks. And I'll add mine to that. It's been a fantastic talk for Space Week. If you want to stay with us while we talk about comets and other things, please do. If you have to rush off, I understand you had a very busy day yourself. No problem at all. So
yeah, I'll stick around and I'll just answer any questions that pop up in the chat, but I'll take myself a video and mute myself.
Yeah, while I'm talking, anyone wants to type any questions, we'll come back to them after this, because I'm going to keep it brief, because most of it is in the magazine. I'll start briefly with the comet, which is the big story at the moment. Comet Tsuchon-Shan, I think is how you pronounce it, -Atlas. It's from the Chinese observatory called Purple Mountain in English, or I'm calling it Comet TA for short. That's much easier. So Comet TA was found 2023, and it swooped quite close to the sun and is passing between the sun and us. It was closest on the 27th of September. By the way, there's a full article in the magazine explaining this. If you miss it, I'm going to go fairly quick. And it'll be near the sun in the daytime sky and extremely dangerous to look at. So if you don't know what you're doing, don't do this. But some of us who saw Comet McNaught in 2007 doing a similar thing will stand behind a building. The sun is blocked by the building. Just above the roof, you might see the comet in the daylight sky, caused by an effect called forward scattering, where the sunlight is just catching the comet's dust in the right way to brighten it. By a factor probably around 100, it could become brighter than Venus, magnitude -5, if you know what that means. It won't be a very spectacular sight. We don't think. You never know with comets, of course, and we may not see it at all. But the comet certainly is brightening more than expected. Last time I checked, the day before yesterday, it was first magnitude. I've been trying to spot it in morning skies, but Ireland's really too far north. It's much better in the equatorial regions and the southern hemisphere, where they've had this glorious tail, 20 degrees long. That's as long as the plough, roughly, and sending back fantastic photographs. But for us, if you don't want to risk seeing it during daylight, just a few days later, it'll appear in the evening skies. Now, low down at the start, and you'll see the star map in the magazine. And the best thing is to look for the bright stars like Arcturus as soon as the twilight is decaying. You'll see where the comet is evening by evening relative to that star. Sweep the horizon with your binoculars. You're going to want a nice clear horizon. The comet will quickly fade because remember, it's already past its closest to the sun, which is heating it up and brightening it up. And it's moving away from the Earth as well, which will also contribute to it dimming. It should be a binocular object by the end of the month. Moon will come into the sky as well, which is not going to help when we have the full moon later in October. So there's sort of a narrow window of maybe a week, mid-October onwards, when you'll see it. So check out the article in the magazine. Remember, there was a comet during lockdown in July 2020. You'll see that on the front cover of the September issue of the magazine. It was about as bright as the brightest stars in the sky, magnitude 1 or 0. That's Capella or Vega, those kind of stars. Near the plough, I remember the view being incredible. People who couldn't travel but we're in rural skies that could see it from the backyard. Got fantastic views. A lot of people missed it, unfortunately. We certainly couldn't run a comet watch back then for NEOWISE. Other comets have appeared. They've been visible in the southern hemisphere. You might have heard of one called Lovejoy. We never saw that at all. So watch out for Comet TA. We'll certainly be reporting on it in the magazine, and the weekly email will update you as to if you remember the club, as to whether or not it's achieving the targets that most people think it will reach. But comets, they say, are like cats. They do what they want, not what you want them to do. And they have tails as well. That's Comet TA. Check out the magazine article. Planets to see in the sky in the evenings. You've got Saturn high in the south every evening. There's a great link, astronomy.ie/Saturn. If you've got a small telescope, it'll actually show you where all the moons are and what the rings look like at the moment. But we've got a Saturn watch on October 15th, so tomorrow week. So make sure you get tickets for that. Come along, look through some giant telescopes at Saturn when its rings are closer to edge on than they've been for 15 years. Astronomy.ie for more details on that. Jupiter is coming into evening skies now as well. If you stay up after midnight, it's glorious. I was watching it this morning with the aurora, and it was dominating the south sky, almost overhead. And again, if you've got a telescope, you'll get fantastic views. Specific events covered in the magazine with diagrams. On next Monday, the 14th, Saturn is very close to the moon, one moon width away from it. So you're going to be able to see the rings of Saturn and the craters on the moon in a telescope field of view at the same time. So watch out for that. The full moon on the 17th is the Hunter's moon, the Pleiades star clusters near the moon on the 19th. There's diagrams for that in the magazine. Jupiter then lines up with the moon, not particularly close this month, on the 20th, but the two brightest objects in the night sky will be really spectacular to the naked eye. And 3 nights later, it's Mars' turn to line up about twice as close as Jupiter will be. Not as bright as Jupiter, but now magnitude 0. So quite prominent. That should be a nice sight. Check out the magazine. And if you've got binoculars, the day after, the 24th, the Beehive star cluster is near the moon, and the moon's only 44% sunlit, so it's not too bright, swamping out the stars of the faint cluster. Regulus near the moon at the end of the month. And don't forget, at the end of this month, on Sunday the 27th, the clocks go back. So it'll start to get dark nice and early. Isn't that fantastic news? No more daytime sky. Or sorry, no more. You will get to see more of the night sky in the evening. So you'll all be going home in the dark. And then it's Halloween, and we're on into November then for our November lecture, which I'll tell you about in just a second. But don't forget, there's a possibility of the aurora tonight. Every day we'll tell you whether we think there's one coming or not. So make sure you get the magazine, loads of diagrams, more information, all of those things. But some great highlights in October. So just to end, future events, the Saturn watch I've already mentioned, October 15th. Evening classes are on October the 22nd. And they're for beginners, no knowledge of astronomy, science, maths, or anything required. They run for 8 weeks, every Tuesday night for 2 hours, little break in the middle. John Campbell, who's the new editor of Astronomy Island magazine, I'd like to announce. He's a YouTube famous astronomer, and he's been giving classes for a couple of years now. We get fantastic reviews from him. So you'll enjoy those. Book everything on astronomy.ie, including our next lecture, our November lecture, November the 11th, or usually the second Monday of the month. And that's during Science Week. This is Space Week. In November, it's going to be Science Week. It's about the search for Earth 2, exoplanets and life in the universe. Dr. Matthew Bothwell, who's a public astronomer at Cambridge University, is going to tell you all about that. More details on the website where you can book the tickets as well as you did for this evening's talk. So we're going to be kept very busy. Do follow us on Facebook, Twitter, X, Instagram for the aurora alerts. Anything else we'll have reminders of. Weekly email will tell you more. If you're not a member, do please join to get the magazine. We wrote it for you, or we write it for you every month, and tell all your friends to join as well. That's all the announcements. If anyone's posted any questions in the chat box, if Mark's still there, I'm sure he'll have a go at answering them. Box back up. Oh, I think we're good. So thank you all very much. Thanks for coming to our meeting. We'll see you maybe at the Saturn watch if you're in the Leinster area. Apologies, we can't run them all over the country. We will again one day like we used to do in the past. And sign up for our evening classes. See you in November, the November talk. Okay, I think we'll end the recording there.